So, today is the second lecture on this course environmental degradation of materials. Here I will be talking about thermodynamics understanding behind environmental degradation of materials, mainly the corrosion aspect of degradation. Now, in the last lecture we have seen that it is very important to study the mechanism of environmental degradation, the reasons, because it involves a lot of money. Degradation in the sense its loss of material, loss of properties, a loss of appearance, and all this loss finally lead to a lot of money loss associated with this environmental degradation of materials. So, we need to have a greater look at this subject. Now, in the last class we have also seen what are the course structures, and then we have already started the electrochemical aspect of material degradation, and we have seen that there are different forms, and those forms are associated with the forms there are many factors which decides those forms of degradation. For example, one is oxidation, one is corrosion, and corrosion can also be divided into several parts. For example, aqueous corrosion, you have dry corrosion. So, aqueous means aqua means water. So, the corrosion involves H2O, okay, that is basically aqueous corrosion. Now, we have also seen that in the course structure also we have seen that there are microstructure related forms, environmental related forms, stress related forms, even geometry also tries to affect the corrosion. So, let us have a small brief on the forms of corrosion. Let us say in your application, in actual situation, you can have a material. Now, after some time, let us say 1 year, you are seeing that the material, if it is exposed to the environment, you will see that the material has lost some of the material from the outer surface. Okay, the hatch part is already lost or dissolved or eroded due to some reason. Now, you see that the most of the case in all the sections, if you take a section, you will see that the loss of material is happening uniformly throughout the cross section. Now, this is, you can call it as uniform degradation, or if it is corrosion, then uniform corrosion. Then you can also have, let us say you are having one material M1, another material M2, okay. Then if you expose this material, this combination of these two material, if you exposed it to a solution, okay, then you can have, depending on the electrochemical characteristics of M1 and M2 in that solution, either M1 can dissolve preferentially or M2 can dissolve preferentially. Now, that is basically happening because of this coupling of these two different materials, and this is termed as galvanic corrosion. Okay. Now, you have another thing, let us say you have a material, you have a stainless steel, SS steel. Now, you have a rubber band. Now, you put that rubber band in acid media, you will see that after some time this will be into two hubs. It will be broken into two hubs. Now, you will see why this is happening, because if you see carefully, the rubber band is making a crevice in this region, and now corrosion is very much aggravated, or the rate of corrosion is very fast compared to the other surface, is very fast at this zone, in this zone. So, in this zone preferentially the corrosion will occur or the material loss will occur, and then finally you have, and the rubber band also is exerting some pressure, then because of this two combination it can go break into two pieces, because you are having a corrosion, preferential corrosion, that means a sort of corrosion is extending into the material, and then you have the stress you have also the stress factor associated with the rubber band stretching. So now you can have a breaking of this material into two halves. This is due to crevice formation. We can call it as crevice corrosion. Crevice corrosion. Now you can also have, let's say, if you take a brass copper 30% zinc, this alloy, if you expose it to potable water, what you will see that after some time, let's say 1 year or so, you will see that the surface is coming reddish in color. This reddishness, this is reddish, red color is coming. This red color is coming because of you will see, if you study the top surface, you will see that a copper is depositing on this surface. Now if you carefully again observe, you will see that in this region the zinc percentage goes down and copper percentage goes up. If you compare the concentration 70:30, that means 70% copper and 30% zinc, and so copper 30%, from 70% it can go to 90%, from 30% zinc it can go down to 10%. So that means you see differentially zinc is coming out and copper is staying back. This is a sort of de-alloying. Initially you have mixed copper and zinc to form an alloy. Now you are exposing into a solution or the aqueous media. Now because of this effect, zinc is coming out and copper is staying back. So it's a sort of preferential dissolution of zinc from the alloy. That's why it is called de-alloying or de-zincification. So just I am giving a briefing of what are the forms that are available. Okay, then you can also have pitting. Now pitting, you have a stainless steel. Okay, also let us not consider the stainless steel example. Let us take a mild steel. If you take it, if you etch it in nitrile solution, 5% nitrile solution for a longer period, if you etch it, you will see that in addition to the grain boundary, you will see there are some etch pits. There are some black regions on the grain, in the region of grain. So that black regions are basically nothing but etch pits, and these etch pits are forming because of a sort of corrosion called pitting corrosion. Fine. Now you have, that means in some region the dissolution rate is very fast, but other regions there is a sort of uniform corrosion. So if you see this in cross sectional, if you take a cross section, now if you see, let's say you have cut this portion, you have sliced it out. Okay, now if you check it, then you can see that this region, this, if you see from this direction, you will see the crack has, this pit has moved like this. So that means you have almost no corrosion on this regions or uniform corrosion, but the attack is very severe in this localized region. This is called pits. Okay, and it's associated with the pitting corrosion. Now you can have also stress corrosion. That the stress part I will come later, but let us see what would be the effect of velocity. Now the velocity part I have discussed in the last lecture. So if you have a pipe and then you are having a flow of fluid or the water, now if you have a sharp corner in the, or sharp bend in the pipeline, then you can have a sort of corrosion which is the combined action of impinging force because of water which is mixed with dirt material, and that is associated with, that is basically nothing but erosion corrosion. Now you can also have cavitation. Cavitation also I have told a little bit. Now you have a flat surface, you have a water bubble. If it breaks, then it exerts a lot of pressure on the material. So this material locally it will get deformed. If it gets deformed, that means the outside surrounding region is not deformed. The deformed region is high energy region, and high energy region is always susceptible for corrosion attack. So this is called cavitation because of bubble formation and its breaking. Now you can also have fretting. For example, the railway case, one example is that is the railway material. Let's say this is a rail and this is fastened with one fastened with the slipper. Okay, now if you see that when rail is coming, it's getting heated up. Now when train is coming, it's getting heated up and it's expanding. When train is moving out, that means it again cools down, it again contracts. And this contraction and expansion at locally it's happening. So that local portion is having a fretting action, a very small alternate movement of these regions. So that force, and it's also under pressure, okay, under pressure, and then this pressure as well as this fretting action, this alternate motion, it gives rise to a sort of wear, okay. And now if you have, when this friction is happening, that friction leads to high temperature, heat, locally the heat is increasing, and it's also in an environment you have oxygen. So if you have oxygen, if the local temperature increases, the material in this region can get oxidized, and this oxide is very brittle in nature. So oxide, if you have a fretting action, so oxide will move out, so it will expose a fresh material. Now fresh material again would get oxidized, and that oxidation would lead to again the breaking of that oxide scale, and then again fresh material is exposing. So this is happening continuously. So you are having continuous loss of material. So it's called fretting corrosion. Fretting corrosion. Now you have also action of stress. One is stress corrosion. Stress corrosion, let's say one material, one component is under static tensile stress. Static tensile stress. Static tensile stress. Now this stress in the normal component, in the design component, if it should be designed, the design stress should be lower than the yield stress of this material. Now it's lower than the yield stress of the material, so we cannot expect that the material would deform, because the minimum stress I have already calculated on the basis of design stress. Now in this condition, if you have a corrosive environment, that corrosive environment would lead to corrosion. So say in this region some corrosion is happening, and this is under load. Okay, now gradually you will see the cross section is going down. Cross section is going down. Gradually the cross section is thinning down. Now if it is thinning down, now this is depending on because on the basis of say design stress, you have calculated how much load it can carry. Now the load is fixed. But gradually you will see that since the cross section is lowering down or the decreasing, so you are going to increase the stress at this region. Okay, if you increase the stress, once it can go beyond the fracture stress, and that fracture stress then it can break. So it's a sort of static tensile stress you are having, and because of corrosion action you are having a failure of that material in the form of fracture. So this is called a kind of stress corrosion cracking, and stress corrosion cracking always involve static tensile stress. This is stress corrosion cracking. Now that means it involves stress as well as corrosion. Now you can have corrosion fatigue. Let's say a material which is on that material you have alternate stress. Compressive, tensile, that is a cyclic stress is given to that material given to the material. Now that material, if it is associated with the corrosion, then this fatigue factor as well as corrosion factor both can lead to a corrosion fatigue or the material failure. Now you can also have hydrogen induced cracking. Now last class or last lecture also I have said that hydrogen can lead to embrittlement in the material. If it embrittles the material, that means it becomes very brittle in nature, so there is a possibility the material can fail by cracking. So these are the forms which are associated with the microstructures. Important factor is microstructures. Second is environment. Third is stress. Fine, these are the components, major components. Then you can also have associated with this composition. Then you can have, since this stress is acting as a mechanical action, now we have again seen that there could be a surf factor. there could be sub issues. For example, you can have design related things. That is another important factor. There are several factors like this. Okay, those will guide what sort of form it is. Now this part I am just briefing, because this part will be taken care of by Dr. Chaudhary who from IIT Roorkee. Okay, so I am just briefing this just to give some example that what are the examples of forms of corrosion. Now coming to the thermodynamics part, let us see what we have seen in the last lecture. In the last lecture we have started corrosion. Now when we defined corrosion, we have introduced few keywords. One is loss of material, loss of materials. Second one is, now in this case you can also have loss of performance. Let's say you don't have any direct loss of material, but still you can have loss of performance. Let's say you are wearing some, it's let's say silver ornaments. Silver ornaments, if you find that after some time with the use it becomes little dark in color. If it becomes dark in color, because the silver ornament is meant for aesthetics. Okay, if it becomes dark, then it will not show, it will not be beautiful to wear that dark silver ornaments. So that means what is that darkness? Because silver sulfide is forming. This is also a kind of corrosion, but that one is not, we are not getting any loss of material, rather we are losing the surface appearance, or the aesthetic part is becoming, the silver is becoming dull in nature. So that means loss of performance is another important factor. Now you can also have loss of properties. Loss of properties because of either loss of materials, or it can be mechanical. Let's say you are having stress corrosion cracking. This is a kind of mechanical factor. Okay, mechanical issues, or let's say the material is failing without giving any signal. That is a mechanical failure. Or then you can have chemical effect. Okay, that means loss of properties, the chemical properties will get lost. There will be loss in chemical properties, there can be loss in electrical properties. Fine. So that means this is a sort of loss of materials. Now another keyword was, second keyword was engineering material. So corrosion is a loss of material as well as degradation in useful properties of an engineering material, because we are not bothering about anything which is not in practical use. So the material should be in practical use. At the same time we should see that what sort of corrosion is happening, and then we should plan accordingly that what sort of protection mechanism we can think of. But before that we should understand what sort of material is this. This should be engineering material. Now the most important part associated with corrosion is, there is one more keyword which is nothing but electrochemical reaction with environment. Now this is a very important part. This loss of material, or rather loss of engineering material, is happening because of electrochemical reaction with its environment. Now, so now let me concentrate on this part. Let us understand what do you mean by electrochemical reaction. Last lecture I have just shown one example, that iron corrosion. Iron going to Fe++ plus 2E, and this 2 electron is getting consumed by this reaction, and this one and this one, they are combining and forming FeOH(2). Now that time we have seen that this process, it involves exchange of electrons. Exchange of electrons between what? this iron is leaving 2 electrons and giving rise to iron ion, Fe plus 2 ion, then these 2 electrons will get consumed by this reaction, form OH minus ion. So it's a kind of transmit of electron from one place to another. This thing can happen on a material surface. Here it's happening on iron surface. Iron surface, that means what is happening? Iron is going as Fe plus plus. So now it's leaving 2 electron. This 2 electron is coming here. Okay. Now this 2 electron is combining with oxygen H2 plus 4E going to OH minus 4. So that means in order to get 4 electron, you have to have 2 Fe plus plus formation, another 2E. So combination of these two process, it gives rise to 4 electrons. These 4 electrons will be consumed by this reaction. Now we have also seen that this is called anodic reaction, this is called cathodic reaction. Now that means any process which involves transfer of electrons as well as that electron, if somebody is leaving some electron, that electron should be consumed because the charge cannot remain as it is. There must be a charge balance. Now if you see, I have also said in the last lecture that oxidation reaction with M, it can also form MO. This is also a sort of corrosion, but I will come to that why it can be considered as corrosion if we understand what is the electrochemical nature of corrosion. That means from this it is very clear that there should be 1 or 2 anodic reactions and 1 or 2 multiple cathodic reactions depending on the situation, actual situation, but there should be balance in charges. So no charge should remain free. Now if you consider some examples, let us see some examples. This is one example. Let us see one more example. Let us say in a solution, in a beaker, you have HCl which is deaerated. Deaerated means it does not contain any dissolved oxygen and it is also very, very pure. Very pure means it does not contain any other species except HCl. In HCl sometime can be contaminated with Fe3 plus 3, Fe plus 3. This ion can be there in HCl. So this is a sort of impurity in this medium. So we do not have this in this. Now I have put a zinc rod here. If we put a zinc rod, you will see that you take out that zinc rod after some time, you will see that zinc has corroded because there will be weight loss in the zinc. And if you check this media, you will see that there is a zinc plus plus ion. Initially there was no ion of zinc plus plus, but now you will see there is a zinc plus plus ion after some time. What is happening now? Let us investigate this part. Now if you blow it up, the small region here, let me blow it up. This region I have blown it up. Now here, since zinc is coming out, so zinc is coming out, zinc plus plus. Now from zinc it is forming. Now if you form zinc plus plus, there should be 2 extra electrons that is released by zinc atom. So that 2 electron will stay in the in the metal. Now these 2 electrons are extra, so it has to be consumed. Who will consume that? Now at the same time, another observation you can see that when you put zinc in this HCl media, you will see that there are some bubble formation on this surface, and then this bubble will grow and then it will come out as in the form of gas. If you analyze this gas, you will see that this is nothing but H2, hydrogen gas. Now that means hydrogen gas is forming. How would you expect hydrogen gas formation? Now what is the source of hydrogen here? The source of hydrogen here is HCl. If you break it, you will find that there are 2 things, H plus and chlorine ion. Now Since hydrogen is formed, that means must be H plus ion is the source of hydrogen. So H plus, if you would like to go to hydrogen, how would you form? 2 H plus ion can combine 2 electron, go to 1 H2 molecule. So this molecule will move up. So now you see, that means this electron, who is consuming that 2 electron? It is consumed by hydrogen ion. So now this electron is coming here, and then hydrogen ion, 2 hydrogen ion, they are combining these 2 electron, forming H2. Now you see, what are those two reactions which involve electron? One is zinc, which is forming zinc ion, leaving 2 electron, and another one is 2 hydrogen ions are combining these 2 electron, forming H2 ion. Now you see which one is electron accepting reaction. Electron accepting reaction is this, an electron which is being left out by metal ion, that is, this is here, you are basically leaving 2 electron from the zinc atom. So this is, what is this process? This process is nothing but anodic, this process is cathodic. Now what is the thumb rule? Okay, the thumb rule is, or how do you judge which process is anodic and which process is cathodic? If some process takes electron or combines electron, that is called cathodic. Cathodic. If something which leaves electron, that reaction is called anodic. Now this is cathodic, this is anodic. So here this is anodic, this is cathodic. Now the process on the surface where this process occurs, cathodic reaction occurs, that is called cathode. And this process where it occurs, that is called anode. Now there would be confusion. I am coming to that. Say you have one cell, galvanic cell, where you have zinc rod and copper rod. This is zinc rod, copper rod. You have a separator through which charge can transfer but mass cannot transfer. Now you connect this to, what will you see? And here it is zinc sulfate solution, and here it is copper sulfate solution. Now if you see, if you put an ammeter here, you will say that current is flowing. Now current will flow from this to this direction. Fine. Now if current is flowing in this direction, and also you will see some changes here. You will see that copper is depositing here and zinc is corroding in this region. So zinc is coming out as zinc plus plus, and copper deposition. And what is the source of copper from which deposit can take place? That is the copper plus plus ion. So copper plus plus, it combines 2 electrons. It has to combine 2 electrons in order to have deposition. So it goes to Cu, that is on this surface. And zinc ion, where from it's forming? From zinc metal. So zinc metal is gradually coming to the solution. So and by that way it leaves electron. And it leaves electron. So this electron, who will consume? This process will consume. Okay, so if this process consumes that electron, what is where the cathodic reaction is taking place? This surface cathodic reaction is taking place. So this is cathode and this is anode. This is perfectly fine. Now let me see what happens if you have a system where you have 2 electrode. Okay, now you are electrolyzing H2O. When you electrolyze H2O, what you do? You send electrical energy, and then you are getting chemical reaction. The chemical reaction, in one case you will form H2, in one case you will form H2, and one case you will form O2. Which surface do you think you will get H2? This is H2O. And if H2O, that means oxygen should come from this. H2O will break down in the form of H plus plus OH minus. Now H plus has to combine with 1 electron from hydrogen atom, and then again it should combine with another hydrogen atom, which is basically coming from the electron acceptance reaction. So then combines it and then forms hydrogen molecule. Now if it forms hydrogen molecule, that means H plus electron hydrogen, another reaction going to H, so combine H2. Now this is a cathodic process. Now you are supplying current. Which side you think? Now if you see the polarity, this side is connected to a negative terminal. If you think this is a negative terminal, so current will flow from which side to what side? So current will flow, always we know that from positive to negative terminal. Now if you want to see which direction electron is flowing, electron flows opposite to the current flow. So that means electron will flow from this end to this end. So which one is cathode here? Now your cathodic reaction, this electron is coming here, so this electron will be taken care of by this reaction, and this is a cathodic reaction, so this electrode is cathode. Now if this electrode is cathode, the other reaction will occur there, and there oxygen will generate. Now here this is negative terminal because it's connected with the negative terminal. Here it is positive terminal because it's connected with positive terminal. Now you see here the cathode is negative terminal and anode is, the other side is anode is positive terminal. Now come back to again here. Here which one is negative terminal? Negative terminal should be that part which has excess electron. Where we have excess electron? Here you have excess electron. So this must be negative terminal. Now at this negative terminal, what process is taking place? You are having anodic reaction. Fine. Here the negative terminal you are having cathodic reaction. Here you are having anodic reaction. So if you go by the sign of that electrode, then you are lost. Better you should see what should be the cathode or anode. Here it's anode. Anode it becomes negative. Here anode it becomes positive. Here cathode becomes positive. Here it becomes negative. So if you see from this negative or positive sign, then you are lost. Rather you should see which side this electron accepting reaction is taking place and which side electron giving a reaction is taking place. Always this is convention. Wherever you find electron accepting reaction, that will always be cathode, irrespective of the sign. Whether it's a negative or positive, it doesn't matter. If electron accepting reaction is taking place on some surface, this is cathode. Now where this is one and another process where electron is left out, that is anode. Now here in case of galvanic cell, this is anode, this is cathode, because here we have positive, where you have cathodic reaction, here you have negative reaction, or here you have anodic reaction, but the sign is negative here, here it is positive, and this is cathode here, this is anode, here cathodic reaction is taking place here, this is cathode, though its sign is negative, this is anode, though its sign is positive. So go by, that means this confusion always be there. It's better that you go by this convention. Now if you come to this, so you have one region, one region you have zinc. I just remove this, let me again draw it. Zinc is going out, zinc plus plus. If zinc goes out, what happens here? You have a loss of material. So you have a debt. Now this electron is coming here, combining with hydrogen. Okay, so this is the cathode here, the anode here. Because here anodic reaction is taking place, here cathodic reaction is taking place. Now if you combine this, what would be the product? The same way, the way we have done it for iron case, zinc plus plus is going into solution solution, and in the solution you have which is left out. Chlorine is not taking part in any reaction. So, chlorine is left out. So, zinc combined with chlorine, 2 chlorine, it will form zinc Cl2. So, this is my product, and which is the another product? Because hydrogen is also coming out H2. Fine. So, if you want to see the complete reaction becomes now we have from this reaction is pretty clear that there is charge balance, but there is one more balance reaction is taking place. This is nothing but the mass balance. So, we have two major components, one is charge balance, one is mass balance. These two things should be there. And what is the electrochemical nature? There should be one or more anodic reaction, there should be one or more cathodic reaction, but finally the total charge should be 0. So, in case of zinc in deaerated pure HCl medium, there is one cathodic reaction and there is one anodic reaction. Now, let us see one more example where you will see there would be one anodic reaction, but there would be two cathodic reactions. Let us say you have a beaker, you have HCl again, dilute HCl, and in that you have not done any deaeration. So, it has dissolved oxygen. If you have dissolved oxygen, but at the same time it does not have any impurity in it. Impurity means there is no Fe+3 ion in the solution. Now, again you insert one zinc rod. If you insert zinc rod, now again you will observe that zinc is corroding, but if you see, let us say, the same concentration of HCl you have taken and the same time period you have spent in two cases. One case it is zinc rod in deaerated HCl, pure HCl and pure, but here you have oxygen and pure. You will see the same thing here, you will also see weight loss. Now, weight loss means zinc is corroding, and zinc corrosion means zinc is going to zinc plus plus, and on this way it leaves 2 electrons. Now, again you blow it up, this small portion. Now, here you have one case, this portion zinc is going out and leaving 2 electron. These 2 electron go somewhere on the other side. If anodic reaction is taking place, that means zinc ion is forming. If anodic reaction is taking place in some place, so cathodic reaction has to occur on this zinc surface just to take care of this 2 extra electron which is getting generated. Now, who will consume that? There are now 2 sources. One source is H plus, which can consume electron. There is one more source, as you have seen in case of iron, oxygen in the presence of H2O, it can also consume electron and giving rise to OH minus, it giving rise to 4OH minus. So, this is one cathodic reaction, this is another cathodic reaction, that means this is 1, this is 2, and what is the anodic reaction here? This is only one anodic reaction. So, one anodic reaction, 2 cathodic reactions. So, this electron when it comes out from this region, this electron will be consumed by these 2 reactions, H plus as well as O2. Now, if you have this, how many electrons do you need for this? There should be charge balance. How many electrons do you need for these 2 reactions? You need 4 electron and you need 1 electron. So, simultaneously, in order to balance that extra charge, here you are consuming more electrons. So, electron must come from this source, from this anodic reaction. So, more and more zinc ion should come into the solution, leaving 2 electron, more and more electron, and so that electron will be sufficient to take care of these two reactions in order to maintain charge balance. Now, there also would be mass balance. Okay. Now, if you see that there are two reactions like this, so here H plus electron going to H. Now, if you combine two things, so H2 can form, or O2 plus H2O. This reaction also can occur. So, that means here you have to have more and more electrons supplied to this region, because these two reactions consume more number of electrons, and here in one atom if you consider, then it releases 2 electrons. So, it has to release more and more zinc, more and more electron, and on this way you can have more and more zinc dissolution. So, now you see, now if you keep it for the same time duration, let us say 1 month also you have kept it, this one also 1 month, you will see the difference in the situation would be, here the loss of material would be large, would be more, here the loss of material would be less. So, here the corrosion is less, here the corrosion is more. Fine, because we have more number of cathodic reactions and the anodic reaction is 1. Okay. For the time being, you consider in this manner. You will see the greater detail of it when we come to the mixed potential theory. Now, for the time being, you see there are more number of cathodic reaction, there is one anodic reaction. So, anodic reaction should occur more and more, so to take care of this extra electron that is getting consumed by these two cathodic reactions. Now, further let me add Fe plus 3 into this system. That means now you have HCl, oxygen, and then another ion Fe plus 3. Now, Fe plus 3 has the tendency to accept electron. So, Fe plus 3, this Fe plus 3 can also consume electron. One electron it can consume and form Fe plus 2. So, what is this? This is also electron accepting reaction. So, this is also a cathodic reaction. Now, you have 3 cathodic reaction. You have 3 cathodic reaction and 1 anodic reaction. What would you expect? What would be the corrosion rate in this case? Corrosion rate would be more in this case if you have oxygen, if you have impurity. So, gradually you see in this case the corrosion rate would be less. In this the case where you have only oxygen, that case you have little more, and if you combine, if you have one more species Fe plus 3, then again you have further increase in corrosion rate or the dissolution rate. So, that means you see why you think that there is increase in corrosion rate as you go from this to HCl plus O2 and then HCl plus O2 plus Fe plus 3, because there has to be charge balance. Now, the charge balance is basically leading to more and more corrosion in the zinc in order to supply that greater number of electrons that are needed for cathodic reaction to take place. Fine. So, that means you have to have the charge balance and you have to have electron accepting and electron giving out reactions. Now, there are other examples also, but you will come to know those examples gradually. I will come to those examples one by one, but now let me go ahead with the fundamental aspects of it, that is the, before that let me also say the important basic principles of corrosion. Let me point out, one is mass balance, second is charge balance, fine, then third is you have ions going to solution. This is nothing but corrosion and this is nothing but anodic reaction. Fine. Now, these three are very important part of electrochemical natures of this corrosion. Now if you consider what are the components of this section, you have to have metal surface. Fine. This metal surface can be divided into two sections. One is cathode, another one is anode. Here you see this section where anodic reaction is taking place, that is anode. This section where cathodic reaction is taking place, this zone is cathode. So you have cathode and anode. Now second thing is, you have to have a medium where ion can go. So what is that medium? Here the medium is HCl, and this is nothing but the electrolyte. Okay, so you need cathode, anode, and electrolyte. Fine. Now as well as when you have this, you have two different reactions. One is cathodic reaction and anodic reaction. Now in case of cathodic reaction, you have M plus E going to M. Now let us understand this reaction on the basis of oxidant and reductant. If you would like to understand this, let us consider this reaction. What is hydrogen? Hydrogen is a reducing agent. Okay. If hydrogen is reducing agent, that means it reduces something and on the way it gets oxidized. Okay. So if it reduces, that means hydrogen would reduce something and it would get oxidized. Now consider get oxidized, that oxidized part. If hydrogen is oxidized, that means it has to leave electron. If it leaves electron, so this is oxidant, this is reducing agent, because reducing agent will get oxidized, so it will leave electron. If it leaves electron, what species would form? H plus. So H plus is what? This is oxidant or oxidizing agent. Fine. That means this is reducing agent, this is oxidizing agent or oxidant, or this is called reductant. Now in common sense you will see that this is expressed as red and oxidant is expressed as ox. Fine. So if you consider this reaction, you can write it as ox plus E going to red. Now cathodic reaction, this reaction is taking place, this is ox, this is red. And what reaction here it is taking place? This is ox, this is red. Now if you combine these two, what would happen? Those two electrons will get cancelled and then you will have sorry, let me put a different name here, N plus. So if you combine, then M plus N giving rise to N plus M. This is the complete reaction. Now this is what? This is ox. This is what? This is red. Let me give this as red 2. This is red 1. This is ox 1. This is ox 2. So this is ox 1. This is red 2. It is ox 2. This is red 1. Now what is happening here? You are having one reaction where ox is going to red, that means oxidant is going to reductant. This process is called reduction. This process is called reduction, that means every cathodic process is a reduction process. And if reductant goes to oxidant, that is called oxidation. Every anodic process is a oxidation process. So now you have a reduction process, you have oxidation process. If you combine reduction plus oxidation, if you take this part only, then it goes to red ox. So if you combine cathodic and anodic reaction, actually you are giving rise to it will actually have what is happening, one case reduction, one case oxidation, and then if you combine the first, this underlined part is a redox reaction. So in case of electrochemical reaction, you have metal surface, anode, cathode, you have electrolyte, at the same time you have redox reaction. This is very, very crucial thing. You must be having reduction reaction, and that should be coupled with an oxidation reaction, and then combinedly you have to have a redox reaction. So these are the important components of electrochemical reactions. Now coming to one issue that I have not given any, I have said that oxidation is also a corrosion process. Okay, let us understand that part before I go to the actual thermodynamic consideration of corrosion. In case of oxidation, what is happening? You are having M metal, it combines with half of oxygen going to MO. If you see the oxidation number in this case, this is 2 minus, this is 2 plus. Now let me have two sections. One case I have the zinc process, zinc corrosion in HCl. So zinc plus 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 2E zinc. Now this 2 electron, it's combined by H plus plus E H2, and this is oxidation, this is reduction. So combinedly it is basically a redox reaction. What is the anode? This portion is anode on the metal surface, this portion is cathode, because here cathodic reaction or reduction reaction is taking place, here oxidation reaction or anodic reaction is taking place. So now you have all the four components. You have electrolyte here, which is nothing but HCl. You have metal surface, which is cathode. This part is cathode. And now all the four components you have: electrolyte, cathode, anode, and redox. Now let us see here whether we have all those processes or not, all those components or not. Now metal surface, this is metal surface. Let's say we have oxide layer. Now you have MO, you have oxygen here. Now this is gas, this is oxide, this is metal. Now you have two distinct interfaces. One is metal oxide interface, which is this part, and another one is oxide gas interface, which is this part. Now as I have mentioned, there could be diffusion of oxygen ion from outer surface to inner surface, or metal ion can diffuse out. So if and from this, if MO is the oxide, that means there must be metal ion formation, metal plus plus, M plus plus, and there must be oxygen ion formation, which is oxygen 2 minus. How would you form oxygen 2 minus from oxygen? That means you have to add 2 electron, then only it can go to O2 minus. Also here you have to, from metal you have to take out 2 electrons, then form process should occur at these interfaces, at this interface, which is metal oxide interface. So if this process is happening here, this process is happening here. What is this process? This process is nothing but oxidation or anodic reaction. And on what surface anodic reaction occurs? On anodic surface. So here which one is anode? Anode is this. This surface is anode. Now which surface this reaction would occur? This reaction would occur because here you have excess of oxygen. So this reaction must occur on metal oxide gas interface. So if what is this reaction? This is electron accepting reaction. That means this is a cathodic reaction, or this is a reduction reaction. Fine. So reduction reaction is happening at this interface. So what would be this? This would be cathode. Fine. Now let us compare with this. You have anode here, you have cathode, you have cathodic reaction on this surface, you have anodic reaction on this surface, you have electrolyte here. Fine. Now we have come to know that this surface is anode, and on this surface this reaction is taking place, anodic reaction, and this surface is cathode, this reaction is taking place. But how would this reaction get 2 electron? That means initially oxygen is in 0 state. Fine. So there must be some source of electron. The source of electron is this, and this has to pass through this medium. Okay, and this medium electron can flow. So this medium is acting as a conductor. But now if you have these two processes, so electron is coming from this to this, and then it is consuming this. Oxygen is consuming 2 electron, forming oxygen minus 2 minus ion. Now which surface do you think it would grow? The oxygen, if you constantly supplying oxygen, then constantly this surface would keep on growing. Now which surface would grow? It would be decided by where this metal ion is combining with oxygen ion and forming this. Okay. Now if oxygen ion is diffusing through the oxide layer to this surface, it comes to this surface, then it finds M++ ion. So then immediately it will combine with this. So oxide layer growth will take place on this surface. Now instead of that, if metal ion comes from this to this, so through this metal oxide layer, then metal ion is coming here, it again finds oxygen -2 and combines there, it forms MO. So metal ion it diffuses out, then metal oxide forms on this surface. If oxygen ion diffuses in, then metal oxide forms on this surface. Now here which is the electrolyte? HCl. And what is the function of electrolyte? It supplies the charges or the ions. Ions goes into electrolyte, or ions are coming from the electrolyte to the electrode surface. Here if you think that oxide is growing on this surface, metal ion is passing through this metal oxide layer and coming here. So what is the function of metal oxide? It is nothing but electrolyte. So metal oxide is acting as electrolyte. So this is electrolyte. Fine. Now if this is electrolyte, so you have all the 4 components. This is anode, this is cathode, this is electrolyte, and you have anodic reaction or oxidation reaction, you have reduction reaction or cathodic reaction. If you combine these two, then it forms a redox reaction. Fine. So if you compare these two things, this is aqueous corrosion, this is high temperature oxidation, both are having the similar components and similar electrochemical redox reactions is happening. So, this is also a form of corrosion. Thank you.